Welcome to this month's STAAD Coffee Corner. It is October 2021, and we will be discussing how to incorporate the direct analysis method into STAAD.Pro according to the AISC 36016 code. Now let me go over a few brief reminders for our coffee corners here at Bentley Systems. We do typically conduct one coffee corner a month in the US for STAAD. It is typically on the third Thursday each month, and it's at 1 p.m. Eastern Standard Time. If you're not located in the United States, we also do provide STAAD coffee corners and special interest group sessions for other regions of the world. Now let me go ahead and introduce myself. My name is Sabrina Tedeschi. I'm a Senior Application Engineer here at Bentley Systems. I've been with Bentley Systems for 13 years, and I conduct training courses and create training programs for all of the products within our RAM and STAAD product lines. Before working for Bentley Systems, I did work for an architectural engineering firm, designing large commercial structures out of a variety of materials, including steel and concrete. Over the course of today's session, we are going to be focusing our attention on incorporating the direct analysis procedure according to the AISC 36016 standard into STAAD.Pro. We will be spending the majority of our time discussing the different parameters that we're going to incorporate into our model, which we will do through the STAAD.Pro Analytical Modeler. Towards the end of this session, I will also show you how you can incorporate all of these commands and specifications into the STAAD.Pro Physical Modeler. So let's go ahead and discuss the standard which we will be incorporating. The AISC 36016 Chapter C describes a direct analysis method which accounts for the second-order effects resulting from deformation in the structure due to applied loading, imperfections, and reduced bending stiffnesses of members due to the presence of axial load. To start this process, we're going to focus on three main commands or specifications. We're going to ask the analysis to incorporate our second-order effects, including our P large and P small delta effects. We are going to consider the initial system imperfections through the use of notional loads. And we will adjust the flexural and axial stiffnesses of the members as required by the design standard. Now please note this is a nonlinear iterative analysis as the stiffness of the members is dependent upon the forces generated by the load. We will now turn our attention to our sample model in STAAD.Pro. As you can see, I've already created a steel building structure in the STAAD.Pro Analytical Modeler. All of the member properties and materials have already been assigned, along with any specifications, supports, and basic load cases that would be required to fully design this building system. Now, before we get started, one important thing I want to go over is the material specifications. When you ask the program to go ahead and calculate some of these direct analysis parameters, the program will need to know the yield strength of steel for the analysis command. In order to ensure that the correct yield strength of steel is assigned, you're going to want to make sure that your FY field is correct in your material specifications. Now for my particular model, all of my members are wide flange shapes according to the AISC 360 specification, and I've assigned this material property to each one, which includes the yield strength of 50 KSI. If the yield strength field was empty, the program would go ahead and automatically assume 36 KSI, which may or may not be appropriate. Now that we've gone over our sample model, let's go ahead and proceed to the first step in our workflow. Now for this particular model, the first step I typically start with for the direct analysis method is to create my direct analysis definition. Now, your direct analysis definition contains two different parameters, your flex parameter and your axial parameter. Members listed with the flex parameter will have their EI values factored by 0.80 times your tau beta while performing the global solution, and members listed with axial will have their EA values factored by 0.8 while performing the global solution. So let's go ahead and take a look at how to incorporate that in our model. To start this process, I'm going to highlight the direct analysis definition, and then I will go ahead and click the Add button. Now at this point, let me also discuss the current version of STAAD.Pro. Now there have been some changes to how the direct analysis method is incorporated into STAAD.Pro. I'm currently running the latest release of STAAD.Pro, which is STAAD.Pro Connect Edition version 22 update 7. Let's go ahead and get started with the flex parameter. Now what gets entered into this field here? What I'm going to enter is the initial value of that tau beta factor. Now for more information on how tau is calculated, I would encourage you to go ahead and refer to some of the relevant equations in the AISC 360 Chapter C. For this particular model, I'm going to assume an initial tau factor of 1.0. And I'm also going to ask the program to perform an iterative solution to calculate tau while performing the global solution. We're going to instruct the program to perform that iteration when we specify our analysis command. In addition to that, I'm also going to enter my axial parameter. Now, no data is required here, so we'll just click on the Add button and then click Close. If I expand the direct analysis definition, I would see that I've created these two parameters, and now I'm ready to assign them to my model. I'm going to assign both of these parameters to every single member in my model. Now, if I were to take a look in the AISC 360, I would notice that applying a stiffness reduction to some members and not others can in some cases result in artificial distortion of the structure under load and possible unintended redistribution of forces. So for that reason, I'm going to assign both these parameters to everything. To do that quickly, I can highlight the parameter, say Assign to View, and click on the Assign button. Okay, at this point we have finished with our first step in our workflow, which was to assign the direct analysis definition. Now again, what this will accomplish for us is it will go ahead and adjust the flexural and axial stiffnesses of the members as required by the direct analysis procedure. Let's go ahead and move on to our second step, which will be to generate our load combinations considering our notional loads. Now, as I do that, I do like to take a look at what load cases are currently created in this model. This model currently has dead load, live load, wind load, and seismic load. If I double click on any of these load cases, I'm going to notice that the loading type is correctly specified for each one. That will be important if you intend to have STAAD.Pro generate your load combinations for you, which is the workflow I'm going to choose for this session. Now that we've gone over that information, let's also discuss the different types of load combinations that are available in STAAD.Pro, as this may have a significant effect on your overall analysis results. In STAAD.Pro, you can generate two different types of load combinations. You can create your traditional load combinations or repeat style load cases. In a traditional load combination, what that is it's a set of load results which are combined algebraically to produce a superimposed set of results for post-processing. In contrast to that, a repeat load case is basically a new primary load case using combinations of previously defined primary load cases. Now, one of the key aspects of a direct analysis method is that you are required to incorporate second order effects, including P large delta and P small delta. In order to assure that those second order effects are captured during the analysis, it is very important that you generate repeat load cases. Now, you're going to do this anytime in STAAD.Pro where you're performing a second order analysis. So this would be a direct analysis, a P delta analysis, for example, and also any model that contains tension only or compression only members. Now that we've gone over the type of load combinations we're going to want to generate, when we do generate repeat style load cases, we have the option to incorporate notional loads. Now, notional loads are basically a portion of your gravity load that's going to be applied horizontal. And what this does for you is, according to the code, this will go ahead and consider the initial system imperfections. Now, for my particular model, I'm going to go ahead and eventually design my system for the AISC 360 LRFD standard. Considering that information and considering the fact that I'm going to perform an iterative solution for the tau factor, my notional load for this example would be 0.002. Now, when I generate load combinations, I do have the ability to incorporate the notional loads into my load combinations, and it will automatically assume a 0.002. Now, if 0.002 is not appropriate for your particular model, you can go ahead and also manually create notional loads. The best way to do that is to go ahead and create a notional load case through a reference load item. So let's go ahead and turn our attention back to our model where we're going to generate our load combinations. Again, I'm going to use my automatic load combinations, and I can go to automatic load combinations here. I'm going to select my combination table. For this exercise, I'm going to use the AISC 716, and I'm going to select my design category. Here I'm going to select the first category, which will be strength design, where my live load is less than 100 PSF. Of course, you're going to want to review all of your load combinations during the process of generating them to make sure that all your code requirements are incorporated. Now, before I generate my loads, I need to ensure that the program is going to be generating repeat load cases. And when I select this option, you're going to notice that your notional load checkbox is now active. The program knows that notional loads would be appropriate for second order analysis, so that's going to be actually inactive until you tell the program you want to generate repeat load cases. Let's go ahead and select that option here and tell the program we want to generate our loads. Now let's go ahead and take a look at the nomenclature here. So this would be load case number 7. The 1 here would be referring to load case 1. That for this particular model is our dead load. And then here's the factor for which dead load would be. So this load combination represents 1.4 times dead. Then we're going to see some additional information here, which will be NL. This is signaling that notional loads have been added. And we're going to see our load case 1 again. Then we're going to see an X. An X means the direction. So this is going to be the notional load added in the X direction. And here's the factor. Since this load combination refers to 1.4 times dead, basically what the program did was it took 1.4 times 0.002 to arrive at 0.0028. Now what we're going to notice is for each type of load combination, the program has basically generated 4 load combinations. So the first 4 here all represent 1.4 times dead load, but you can see the first 2 are the Notional load adding in the x direction, we have positive x and negative x. And then we also have positive z and negative z. And then you're going to see that same type of methodology as we work our way down. Now, if we're satisfied with our load combinations, let's go ahead and click the Add button and let the program go ahead and generate that for us. Now, as you can see, the big advantage of using the automatic load combination generators in STAAD.Pro is it made the process a lot easier and quicker for myself. Now that we've generated our load combinations, one of the areas that I always like to show when generating load combinations is how to understand the load combination rules. So let's go back here and go to Edit Auto Combination Rules. Now what we'll be able to see from the Automatic Load Combination Manager is we'll be able to see all of the tables that are used when the program generates load combinations, and all of these are supplied when you install the program. Now for this particular exercise, I went ahead and selected the AISC 716, and I selected this table. Now this will go ahead and give me a preview of all the different factors and types of load combinations that I want to generate. Within each code, we also have a configuration option. Now what the configuration option will do for you is it'll go ahead and show you what types of combinations it'll create and what types of loads are considered candidates for notional load. So here from this table, we can see that dead load, live load, roof live load, snow load, and ice load are all candidates for notional loads, which basically means that the program will take 0.2% times those loads and apply them horizontally when those types of loads are included in a load combination. Now the last thing we're going to do is we're going to go ahead and move on to our final step, which is to incorporate our second order analysis through a direct analysis command. To do that, we're going to go to our Analysis tab in our Page Control area and then click on Define Commands. Now in the Analysis Print Commands dialog, we're going to see all the different types of analysis that can be performed in STAAD.Pro. And let's go ahead and select the Perform Direct Analysis option. Now what's important to understand is that the direct analysis method is requiring us to incorporate both P large delta and P small delta in our analysis. P large delta considers the second order effects induced on a structure due to the movement of its mass under lateral loads, and P small delta effects are the effects caused by the displacement of the members between their bracing points. Now by default, when you invoke the Perform Direct Analysis command, the program will automatically consider both your P large delta and P small delta effects, so I don't need to enter anything else to make sure that that happens. I do need to enter a few other parameters, however. The first thing I'm going to do is I'm going to enter my option. Again, I'm performing my analysis and eventual design according to the LRFD portion of this specification, and I'm going to make sure that that is entered. In addition to specifying your analysis options, you're also going to tell the program how many iterations you want to perform. Now, I typically recommend performing anywhere between 5 and 25 iterations, and it is important to remember that a direct analysis will always be a non-linear iterative analysis, as the stiffness of the members would be dependent upon the forces generated by the load. Now, as it performs the iterative solution, it'll look for convergence of both my tau factor, if I'm performing a tau iteration, and also my displacement or my P delta. I'm going to go ahead and ask it to perform iterations for both. I'm going to instruct it to reduce my EI value. That'll make sure it looks for that direct analysis load definition. And finally, I'm going to perform a tau B iteration. Let's go ahead and click on the Add button to complete that process. Now, if I were to take a look at the end of the input file, I would be able to see my Perform Direct Analysis command has been added with all of the information that I provided when creating this command. Now at this point, for this particular model, I'm ready to go ahead and perform an analysis. Now please remember that again, this is an iterative analysis. It may take a little longer than performing just your typical standard first order analysis. So after your analysis is complete, you're going to go ahead and take a look to see if you have any errors and warnings, which would be displayed in this dialog. For this particular model, I don't have any errors or warnings, so I'm ready to proceed on to the rest of my analysis results. Now, the first place I typically go is to the output file when discussing my analysis results. And there's one key area that I want to point your attention to. When the analysis is performed, basically what the program is going to do is perform an iterative solution to calculate both the P delta and the tau factor for each individual load case. Through the output file, we can go ahead and see if that information has converged, which is what we're looking for. And as you can see in this particular model, it went ahead and performed that iterative solution, and it's letting me know that it has converged. And if I would take a look at the rest of the load cases, I'd see that that's the case for all. So at this point, I notice that I have performed a sufficient number of iterations, and it's safe to go ahead and review the rest of my results or move on to the design phase. Now that we've gone over how to incorporate these parameters in the STAAD.Pro analytical modeler, let's also discuss the STAAD.Pro physical modeler, because you can also perform these same commands or add these same commands and specifications through the STAAD.Pro physical modeler now. Now let's go ahead and discuss the STAAD.Pro physical modeler in case you're newer to this workflow. So the STAAD.Pro physical modeler is used to model your structure using physical elements. The physical model is used to draw structural elements as they are physically constructed. The program will then decompose this into an analytical model, which is passed to the STAAD.Pro analysis and design engine. Now, using a physical modeler workflow, you're going to create everything from your model geometry through your analysis commands directly in the STAAD.Pro physical modeler. Once you're done with those steps, you would then build your analytical modeler, or basically ask the program to build your analytical model, where you'll be able to specify all of your steel design parameters and commands and perform your analysis. If your model did contain some concrete systems, I would also recommend, after the analysis, transferring some of that data over to the STAAD.Pro RCDC, or basically your STAAD Advanced Concrete Design workflow, to proceed with the design and detailing of your concrete elements. We will now turn our attention to the STAAD.Pro physical modeler. And as you can see, I've already created a structure that is identical to the model we were just looking at in the analytical modeler. It contains all of the members, section properties and material information, as well as all of the load items and primary cases. So let's go ahead and get started with the first step of our workflow, which is to incorporate the flex and axial parameters into our model through a direct analysis load definition. To do that, we're going to decide which members to assign those parameters to. And for this model, we're going to assign them to all of the members in our model. I have selected everything. Then I will go to the Member tab in the ribbon toolbar and tell the program I want to assign some direct analysis attributes. While I'm doing this, I'm going to enter my initial value of my tau factor, which is 1.0 for this exercise, and I'm going to tell the program to assign the axial attribute. Now, if you'd like any additional information in any of the dialogues that you're working on in the STAAD.Pro Physical Modeler, you can go ahead and click on the Show Help option, which will give you some additional information regarding the parameters that are available through that dialog. Now, if I'm satisfied with the information, let's go ahead and click OK. Now, all of the information that is added to a STAAD.Pro Physical Modeler is entered through a series of spreadsheets. You can review any of the spreadsheets by clicking on the Spreadsheet tab in the ribbon toolbar and then selecting the appropriate spreadsheet, which are organized in different categories. If you would like to review the direct analysis attributes that you just assigned, we can see that through the direct analysis attribute spreadsheet. We can see that an initial tau factor of 1.0 has been assigned to all the members, and the axial checkbox is selected. Let's go ahead and move on to the second step in our workflow, which is to generate our load combinations. We're going to remember that we are interested in creating repeat style load cases for our load combinations, and we are interested in incorporating notional loads. To start this process, let's go to the Loading tab in the ribbon toolbar and click on the Automatic Combinations icon. Here I'm going to select the code I am interested in and the table. Now the code and the table are identical to the one that is used in the STAAD.Pro Analytical Modeler. In addition to that, I'm going to include my notional loads, and I'm going to enter a notional load factor of 0.002, which is appropriate for this particular model. If you would like more information on the code or table, you can click on the Manage Rules button. Again, the Load Combination Manager is identical in the STAAD.Pro Physical Modeler as it is in the STAAD.Pro Analytical Modeler, and these are the load combinations that are installed with the program. Again, I can see the table that I am working on and also take a look at the configuration area if I would like more information on how notional loads will be incorporated. If I'm satisfied with all of my automatic combination information, let's go ahead and click OK, which will ask the program to generate those load combinations for us. When you generate your load combinations, the program will automatically switch your view to the load combination spreadsheet, which will show you all the combinations that were generated. In addition to that, if you would like your notional load information, you can also review that through the Manage Notional Loads spreadsheet. To access that spreadsheet, I'm going to select the Spreadsheet tab in the ribbon toolbar and click on the Manage Notional Loads area, where I can see all the notional load factors and the directions for which they're being applied. Now, before I finish this step, I'm also going to remember that it is very important when performing any type of second order analysis that I'm generating repeat style load cases versus traditional load combinations. To ensure that is specified in your model, you're going to select the Data tab in the ribbon toolbar and then click on this Options icon. The analysis model options are available for you to go ahead and review how the analytical model is going to be created and to make any changes as necessary. The field that's most important for the step in the workflow that I'm working on is this combination load cases option. Through this field, you can tell the program whether or not you want traditional load combinations or repeat primary load cases. I'm going to ensure that repeat primary load cases are specified, which would be required for a direct analysis. To finish this off, let's go ahead and click OK. I'm now ready to move on to the third and final step of incorporating the direct analysis into my workflow in the STAAD.Pro Physical Modeler. To specify my analysis commands, I'm going to go to the Loading tab in the ribbon toolbar and click on my Analysis Commands icon. Now for this particular model, I'm going to be performing a multi-run analysis. I'm going to analyze each of my seismic load cases individually and then perform a direct analysis on the entire model. As you can see, my first two analysis commands for my individual seismic load cases have already been specified, and the appropriate seismic load case has been assigned to them. Let's go ahead and work on our overall analysis command, which will be our last analysis command in this dialog. Here we're going to specify the analysis type as the AISC direct option. We're going to enter the LRFD option, which I've already decided is the workflow I am using for this particular model. And I'm going to enter the number of iterations. I'm also going to tell the program that I'm interested in reducing the EI during the global solution and that I'm interested in performing an iteration on my tau factor. The last step to specifying your analysis command is to go to your load conditions area. Now within the STAAD.Pro Physical Modeler, every load case or combination must be assigned to an analysis command, and each load case or combination can be assigned only to one analysis command. My first two analysis commands represent the analysis commands for analyzing my seismic load cases individually, and those have already been assigned. You can also see that all of my primary load cases have already been assigned to my direct analysis command. To ensure that my load combinations are also brought over successfully to the analytical modeler, I want to also ensure that those are assigned as well. So everything over here, I'm going to move over to the selected area. Now every single load case and combination has been assigned to one analysis set in my model. To finish off this process, let's go ahead and click OK. And as always, we should save before translating this over to the analytical modeler. Now at this point, we have finished incorporating our direct analysis specifications and commands into our STAAD.Pro Physical Modeler. So let's go ahead and translate this over to the analytical modeler. To do that, you're going to go to your Model tab in your ribbon toolbar and tell the program that you want to return to the analytical modeler. Every time you return to the analytical modeler, what the program will do is it'll go ahead and recreate your input file. Everything from model geometry through analysis commands are specified in this area of the program when you are using a physical modeling workflow. Within this dialog, I can see that the process was completed successfully, and we'll click OK and tell the program we want to return to the analytical modeler. Now at this point, I'm back in the analytical modeler. And before I go ahead and perform an analysis, I do like to go ahead and review the information that was created in my last workflow. So let's go ahead and check on step number 1, which was incorporating our direct analysis definition into our model. As you can see, my flex and axial parameters were successfully assigned through the STAAD.Pro Physical Modeler. The next step I performed was to generate repeat style load cases, which also consider notional loads. If I were to expand my load case details section, I can see that I do have repeat load cases, and I can see that notional loads were also incorporated. The final step in my workflow was to incorporate the direct analysis command. Here I can see that I'm analyzing each seismic load case individually, and at the end of the input file, I can see my direct analysis command has been specified with all of my appropriate analysis options that I selected. Now at this point, I'm ready to go ahead and perform my analysis and then move on to the design phase. At this point, this concludes our process for incorporating the direct analysis methodology into our STAAD.Pro model. We showed you how to incorporate that into both the analytical modeler and the physical modeler for today's session. At this point, I want to thank everyone for coming to our coffee corner today. As a reminder, we do typically conduct one coffee corner in the United States for STAAD.Pro each month, and you can sign up for future coffee corners through the Bentley events page. I'm also going to encourage everyone to go ahead and subscribe or follow our RAM and STAAD wiki through the Bentley communities, and you might also want to consider subscribing to the Bentley Structural channel on YouTube. By doing that, you will go ahead and get updates whenever new information is available. At this point, I want to thank everybody for coming to today's session. Hopefully you will find this coffee corner to be useful and applicable to your particular workflow. And I hope everybody has a good rest of your day and stays healthy. Thank you again, and please feel free to come to our future coffee corner sessions, which again are always complimentary.